I'm not going to talk so much about the specifics of model-based software engineering as the environment in which we're trying to do modeling and the challenges of doing modeling in a modern large system. And I'm going to talk more about large healthcare IT systems because everyone else is probably going to focus more on IT medical or medical devices. So I'm going to go into the big healthcare systems that run hospitals and clinics and other kinds of systems. And there's a huge challenge there. It's a very different world than people trying to build software for medical devices. So let's look at kind of what's happened in the past. 25 years ago, back in the late 80s, the Atomic Energy Group in Canada put out a system called Therac 25. Does everybody know Therac 25? If you don't, you have to read that article. It will terrify you. It will make Frankenstein look like a children's bedtime story. Therac 25 was a device for radiation treatment. It was the first time they went from hardware controls to primarily software controls. Since they moved to software controls, they assumed that they could do all of the locks that kept too much radiation from being released. They could now do all of that in software, so they took it out of the hardware. The software was amateurish. They had a kid build it, basically, who didn't really know much about software development. As a result, they killed several people, and a number of other people received so much radiation they were severely poisoned, scarred, and it was just a disaster, and the lawsuits basically put them out of business. It's just a horror story of lousy software engineering. They didn't model things. They didn't do integration testing of hardware with software until they were ready to deliver the device. And so it was a complete embarrassing mess. Read the story. It really gets into Nancy Leveson, the lead author, is over here at MIT. She's one of the world's gurus in software safety. And so it was just an elegant and excellent sort of recapture of what happened and why it happened and what the problems were. And we've learned a great deal from that. And so having learned that, we're never going to allow that kind of software disaster to occur again, right? I mean, that was 25 years ago. We've learned so much. We've improved so much. We're never going to see another major software disaster in our lifetime, right? Well, the same thing happened in Healthcaregov. It's not a medical device. It's not going to kill you. It might kill the presidency. But the bottom line is we had the same kind of problem. The requirements were being changed up until the last minute. They never had complete requirements. They had 2 weeks to test this monstrously complex system, which essentially is no testing. The code in the interface was amateurish. Now we're discovering the code behind it's probably amateurish too. In fact, they asked me to be on TV several times to explain what's going wrong with this and why and can we recover from it. And the bottom line, I said, yeah, of course we can recover from it. We can redo the browser interface to solve some of the performance issues, and then you'll get the next wave of defects beyond that. We'll fix those, you'll get deeper in the system, and we'll get the next wave of defects beyond that. In fact, now we're finding that when you enter your data into the system, if you qualify for a subsidy, you can in fact get back 5 or 6 different versions of what your subsidy is going to be, completely different numbers, which means that your subsidy is not a number, it's a random variable with multiple answers that you could hopefully choose the best one from for your situation. So the bottom line is we didn't learn anything in healthcare.gov, by the way. We knew all of those lessons. The biggest problem that people haven't talked about is the law was slammed through so fast without time to review it that the amount of conflicts inside the law itself are going to make the system that implements it a complete nightmare. And we're starting to see some of those conflicts written into the law that they didn't have time to test out. I mean, the law itself should have been the subject of model-based systems engineering. They should have modeled the law to see where the conflicts were, because those conflicts will now be built into the system and into the code itself. So we really are still facing these kinds of monstrous software problems. And in the IT world, we don't see as much modeling as we do in the medical device world. Why? A lot of reasons. It's not common industry practice. For a while I worked for Borland, which had a wonderful model-based software system engineering technology called TogetherSoft. It was a big UML modeling environment. You could build elegant models of the system, test various properties of the system using it. We couldn't find that more than maybe 5% of all development organizations were modeling anything. They just don't model. And of those, the ones that did never built complete models. And of those that built a complete model, they never updated it as they changed the system. So the models were typically, by the time you saw them, they were out of date, incomplete, never really used the full analytic capability that these kinds of models offered for analyzing the properties of a system. So I have a question for you. What is the most commonly used modeling tool in the IT world, healthcare or any other part of it? What's the most commonly used tool? A napkin. Yeah, well, that's probably true, but let's go with automated tool. Let's go with automated tool. Yeah. You're dead on. It's Visio. Give the man a cookie. It is Visio. I mean, and there's no analytic power in Visio. It just lets you throw some graphs up and tie some things together and look at it and talk about it. But it's not an analytic tool that gives you much analytic power. So now, how many of you are in organizations that are starting to use agile methods? Yeah, okay, a few hands are going up. Agile methods focus on the code and take a lot of the emphasis off of design. And now if you're in an organization that still focuses on design, wonderful. But the fact is the agile world is a code world. It's not a design world so much. And they say, look, design is going to be emergent, so they really focus on code more than models and don't put a lot of upfront time into modeling systems. My own sense is that healthcare has lagged other industries. In the 30 years I've been in it, when I go to conferences, when I see things, healthcare, not so much medical devices, but the healthcare systems world has lagged other areas like financial, telecommunications, retail, and other areas. Has lagged in the adoption of modern software development and software engineering practices. Medical devices is ahead of the IT side of healthcare. Why? Because that's where the engineers are, and the engineer is to model, right? So, what are the resistance to modeling? Number one, there's a lot of resistance. This is especially true in the agile world because we were required to do so much documentation, and so much of it was never used. I mean, one study I saw in one large corporation, 25% of all the documents produced were never touched by anyone other than the person that developed it. And about another 25% were touched by one other person and not used for anything important. So the bottom line is there was a real negative reaction to why am I producing all this design documentation if nobody's going to read it, nobody's going to use it, why don't I just start building code? Number two, few software developers in the IT side of the house, in the healthcare system side of the house, are trained as engineers. In the medical device side, they are. I mean, I started my career in GE Space Division, part of GE Aerospace. And as medical devices started to move into the digital world, GE Medical came over to Space Division and started trying to transfer a lot of our top guys over into the medical world so they would have engineers who understood systems engineering of software, hardware, combined systems. And those folks modeled. I mean, to be an engineer is to start building models from the beginnings. But that's a problem as we move more to the IT side. A lot of them aren't even computer scientists. They're just guys that learned how to spell Java with less than 4 A's. We did a major study when I was at MCC, the 5th generation computer research operation in Austin, and we went out and interviewed 19 large system development projects, and a lot of these were telecom and aerospace and a number of other, and these typically were hardware, software systems, and we interviewed the design teams. What are you guys actually doing? And describe it, and we went through lots of issues, and what we learned is that it was a very thin spread of domain knowledge. By that, you know, I may know how a computer works, but I don't understand how telecommunication systems switch calls. I may know how to write COBOL, but I don't know how a bank conserves money and transfers money around. There's all kinds of things about the application domain I don't know, and we found that knowledge was very thinly spread across the development teams, the software development teams. So that's a problem because if I don't understand the domain, it's really a struggle to try to model it. In fact, what we were seeing wasn't that these folks were modeling as much as they were trying to search. It was a search process. I'm trying to search for knowledge I don't have so I can at least try to understand what this thing is I'm trying to build. Many developers just aren't system thinkers. They want to start at the lower level because that's what they're comfortable with, and they'll build up to a system as opposed to model the system first and then gravitate down towards the details in the code. Modeling takes time, and the business is screaming for results. Give us code, give us a system, give me more functionality, right? And the demands are great. Too often the schedules are too short to build something that works. And so when there's too much demand, I just start coding. There's that classic cartoon, probably the greatest in the history of software development, where the manager's walking out of the room where the coders are and says, you guys get to coding. I'm going to go down and find out what the requirements are. Emergent design is the new mantra, that the world is going to change. So if I try to do a design up front, model all this stuff, build all this, it's going to change anyway. So why waste all this time up front? Let's just start building the system and watch the design emerge from that, and we'll be making changes to it, and it will continue to emerge as we go. Yeah, but if you start with garbage, what's going to emerge from that is more garbage. The bottom line is, I don't believe in emergent design. I haven't seen it work very well. The fact the guys that do this real well model the system up front and know the areas where they think they're going to suffer the most change. And they prepare for that by trying to look at what are the alternatives that's going to happen as technology continues, and they'll try to protect those areas so that there's some stability in the system and those areas can be more easily changed in the future. So, emergent design is a nice thought, but the truth of the matter is the good folks model first and model where the most risk is for system change and emergent technologies. And finally, management ignores the cost of quality. We got to get something out, and they just don't pay attention to the fact that if I produce garbage now, if I made big mistakes, if I have to go back and do a lot of rework, the cost is staggering. And you know, Lord knows what did they start with? $100 million for Healthcaregov. They'll spend over $1 billion before it's done, right? 10 times the cost because of the mess they made when they started. They didn't model things. The data's not hanging in together like they thought it would. They're trying to put all these systems together that weren't designed to work together when they started. The biggest problem we've got to modeling is we are now in a culture of code, right? And so to drive model-based software engineering into the sort of non-healthcare device world, into the healthcare system world, we're going to have to fight a culture. We're going to have to overcome a culture that's growing stronger because more of the developers think in the agile way, I need to be getting code now and the design will emerge over time. And to really do a good job of modeling and avoid some of the severe problems with large systems, and I'll have some data on this at the end, we're going to have to overcome a culture that it continues to grow in this environment. So, a lot of developers want to talk like they're an artist. In fact, some say I'm an artist. I build elegant code. My programs are beautiful. They're elegant. They pass all my unit tests. I get all this freeware off the net that'll test the structural aspects of it. It passed that. It's beautiful code. I submit it to the build, and it works, right? And they claim that they are artists because they can build elegant code quickly. Bullshit. Right? I mean, the bottom line is, no, you're not an artist. What do artists do? My daughter's an artist. I watch her work. What do artists do first? They build models. And MBSE is over 400 years old. Why? Because here's Bernini, back in the early 1600s, building a terracotta model before he ever submitted this to marble. Right? And he would build a model, and the marble was never exactly what the model was. He'd look at it, he'd look at the perspectives, he'd look at how he wants to represent things, he'd invite the patrons in and get their reaction to the terracotta model, and then he would finally submit this and commit this to marble. Right? Artist model. You can go look at all the great works of Rubens. He's got drawings for everything that's in them. He did hand drawings to get a sense of what his perspective and everything they modeled. MBSE has been here a long time. We just used to call it model-based sculpture engineering. Right? So the culture we've got to create really is one where I am an artist because I model before I commit to code. Artist model first. That is the essence of being an artist, is trying to understand what you're going to create before you commit to creating it. So software developers, 99% of them are not artists. They're the antithesis of an artist. All right, so this is the problem we're facing in these systems. And I can understand to some extent why there's some resistance to modeling in these kinds of large IT systems. I've got a developer building his or her components, really doing a nice job of it. They're competent at Java, and they're building the components to go into the system. They're building, let's say, the business logic for some large hospital management system. And they're part of a team or a project where I've got lots of people building parts of Java, right, building components in Java that come together to perform the business logic of the system. The problem is that is not a modern application, that's an old application. The old applications, I build everything in mumps or COBOL and I'm done, right? But a modern application is a stack of technologies, in different languages, in different layers, that all have to come together, and they may not have been built by the same organization. You go into a lot of these large systems, there's multiple contracts, especially in the government environment, multiple contracts to multiple different organizations that are building different components of it. I mean, there were a lot of people lined up before the Congressional Committee testifying by Healthcare.gov, each one of them pointing at the other guy saying it wasn't my problem, right? So these are, I may have some, a user interface language, JSP or ASP. I've got Java or .NET in the business logic. I've got some frameworks I've pulled out of open source to help make that simpler to work with. In middleware, I've got SQL or some other kind of a query language going down to a database. I know this. I may not understand the database. I may have to go off to some ERP system that's customized in ABAP or some other language. I might be going off to some old mainframe-based system that's written in mumps. Right? And if you want to learn mumps, you have to go to the Department of Ancient Languages or the Department of Archaeology. So this is the problem of modern systems. No single individual can understand all of this, right? And when I've talked to architects in large healthcare systems, their complaint is, look, my problem is not the code. My problem is the interactions between the layers, because guys building this were making assumptions about that, and most of the assumptions were right. It's the ones that are wrong that are breaking the system, because they can't know everything because of the complexity of the technology stack. And I need a way to model this, and then I need a way to go evaluate this once it's built. But if I can model it and see where these assumptions are wrong, for instance, I assume there were timeouts in the middleware. Guess what? There weren't any timeouts in the middleware. Now all the threads are hung, and people can't use the system effectively. So there's all these kinds of problems. This is one of the major issues in modern large IT systems, especially in the healthcare world, where we're trying to build these to coordinate. I mean, just look at what we're trying to coordinate in Healthcare.gov, stuff in Social Security, stuff in Homeland Security to see if the person's even an American citizen, things from 50 or 60 different insurance companies, local state Medicaid systems. I mean, it's just a massive systems that were never designed to work together, written in lots of different languages. So we're in the system of systems world where the challenges now are critical, and just an attempt to model that at least start showing us where some of the inconsistencies are. So this is an oversimplified model of kind of doing domain modeling, right? I mean, if you went to the Encozy website, you'd find a much more sophisticated notion of architecture modeling and behavior modeling and some of the areas you have to model. But let's just say for a minute, I'm trying to build a model of the domain itself, which the developers don't have necessarily a deep understanding of, and our knowledge of how we want to architect systems in our environment to implement that domain. And then if I get that design hooked together, I can send it down and we'll implement that in hardware, software, systems and what have you. And then the system artifacts, the software, the documentation, the user manuals, and everything else comes out of that. And that's the notion of systems, model-based systems engineering, is that we kind of do this mapping up front between the domain and the Now, we did a study of what system engineers actually do when I was at MCC. We went down and looked at the design process. We interviewed a lot of these folks and got them to talk through how they went about it. We actually videotaped people trying to solve certain kinds of system engineering problems. We videotaped a team trying to build a very complex system over time. And what we came up with, what we learned, is that that's kind of exactly what the guru system architects do. The difference between the guru architects and everybody else is they have a very sophisticated model in their head of the domain and how the components of the domain fit together. And they have a reasonably good understanding of the computational world. And they're able to do that mapping. And they're able to do it very effectively. They'll tell you they can't write optimized code. That's what their coders do. But they understand how to design, how to model the domain and map the domain into computational structures that will implement the system. Now, this is what we only found one of these gurus that really had this capability to do it really, really well on 1 out of every 3 projects. And the companies were showing us their best projects. So it's not even 1 out of 3. These are not common folks out there. And that's a huge problem. And so what you typically have is somebody who doesn't have a full model, who's struggling and searching to try to fill this space. And then try to build a model, so the models will be incomplete. Their ontologies may not be really a real reflection of what the real world's like, which means the system's going to come out not mapping to the real world well, and as the real world changes, the system is going to be kludgy to change. But this is what we found. It's not unlike what we're trying to do with model-based system engineering. Since the knowledge required exceeds most human capability, we need the tools. They really have to use tools in order to start trying to capture where does my knowledge fall apart, where do I not understand things, how things ought to hook together. Can I build a model that somebody else can look at and say, you know, you really have forgotten major things here, or this is not going to hook together the way you think, or other kinds of issues. But that's kind of what we saw in the actual human world, in the cognitive world, and how it reflects into the sort of the concept of model-based software engineering. So we're in what I would call the fourth wave of software engineering. So I'm going to get into some of the things we've tried to do to solve some of these system development problems. The first wave was back in the 70s. A few of us with gray hair remember this, where the solution was going to be third and fourth generation languages. We're going to have higher level languages because if you're writing, you know, if you're writing stuff like assembler, who can understand that? It's a write-only language, nobody can read it. So with higher level languages, we could see what was being written into the code, we could understand it, we could evaluate it. That was going to solve all our problems, and if we did it in a way that we call structured programming, it was elegant, readable, and more easily tested. And that was fine, and then all of a sudden, as we moved through the 70s, and the systems got larger and larger and larger, and languages was no longer enough, so the next wave in software engineering was design tools and computer-aided software engineering tools, right? So we had these design methods and the tools that would implement the design methods, and we were told if we would just spend several $1 million on case tools, we would get an order of magnitude improvement in productivity. And by the mid-'80s, it was clear that what we were getting was about a 10% improvement in productivity, right? And so those of us I was at MCC at the time, we were convinced what we really need are better languages and better methods and better tools. So we continue to try to work on better design techniques, better methods, and better tools to really get this promised order of magnitude improvement. There was one guy out there that said, all of you people are crazy, that's not the problem. The guy was a fellow named Watts Humphrey. Watts had spent 27 years at IBM. At the end of his time at IBM, he left, came to the Software Engineering Institute, and created something called the Process Maturity Framework. Because what Watts was telling us is the tools are irrelevant at this point. You're giving people schedules they cannot possibly achieve, making commitments they can't meet, and as long as they're slamming out code as fast as they can to meet an idiotic schedule, no tool, no language, no method is going to make a bit of difference. They're just slamming out code. They don't even have time to learn the tools. So Watts drove us into the next wave, the third wave, which is process. And that I led the team that built the CMM at the SEI based on Watts' original process maturity framework. The operations side was creating ITIL, for those of you who know IT operations, which was how do you manage the service you're providing to the hospital or the bank or somebody else. We had agile methods started towards the end of that decade to say, look, trying to do this as one big swallow, where you spend 2 years building the system and then find out if it works or not, is dumb. You really need to try to break it up into pieces and deliver it in increments and test those increments to make sure they work, so you find the system problems much earlier. So that became the and that was the process piece. At the same time, in the business side, people were starting to do Six Sigma, which is essentially the same thing as CMM was at the higher maturity levels. Six Sigma apply lean principles to try to understand the process and continue to improve it. At some point in a Six Sigma implementation, you ran out of runway. You'd done all the things you could to get the most benefit out of process improvement, and you had targets you had to hit for the amount of benefit, and so we realized now we have to take a step somewhere else. And so they created design for Six Sigma, the notion being the next step comes from improvement in the product, not the process. I'll make a product that's more manufacturable, that's less prone to defects and what have you. So the wave we're in right now really is the product wave, is the fourth wave in software engineering. That's where things like a focus on architecture, you hear a lot about service-oriented architectures, focus on the quality, the structural quality characteristics of software, reusability of components and other kinds of things fit. MBSE fits in here as well because it focuses on how do we make sure we're building an infrastructure, that it's actually going to work in actual use. So that's where we are today. I'm going to talk about a couple of things. I'm going to talk about the domain itself more in terms of process, and I'll come back and talk about the product very much in terms of the quality, in terms of the product issues. So let's jump for a second over into what the CMM was. This was an attempt to fix the problem in software engineering. At least it gave us a huge jump, because Watts' vision was, look, The problem you've got right now, level 1 is where most companies were. People were given commitments they couldn't possibly meet. Have this thing done by Christmas when it'll take 4 years to actually build. Healthcare.gov was exactly it. Healthcare.gov is one of the most level 1 projects in history. Let's just slam this thing out on a schedule that can't be met. Oh, and by the way, you have 2 weeks to test this monstrously complex system. So it was a set of management commitments. They were changing requirements to the very end. There was no control over how they changed requirements. And so that's the kind of situation. And in that environment, no tool, no technique, no method is going to make a bit of difference. You simply don't have time to do professional work. First thing we had to do is give developers a chance to act like professionals. And that's what level 2 was about. The next step was it's not a technical step, it's a management step. It says management must get control of commitments, and they must get control of baselines, and they have to give developers a chance to do their work in a professional way. And the minute they started doing that, all of a sudden there was radical reductions in rework. The quality of the code started getting better, right? But it was really, this was Watts' unique insight. I've got to get management out of the way first. I've got to get them under control and get them to stabilize the environment. Once that happens, now projects may be doing it very differently. They may have different design methods, different tools. That's okay. They're stable. They can do professional work. The next step was to say, look, let's look at what's working best in our environment. These guys have good design techniques. Those guys have good testing techniques. Back there, they've got some good estimating procedures. Let's integrate this into the best practices for how we do our work in our environment. And that was level 3. Let's come up with a common process where I can get an economy of scale, where if I move from one project to another, I still have reasonable expectations about how we perform our work. And after that's in place, when you look at the house of quality in Toyota, the one thing it's built on is an assumption of standardized processes. If you don't have standardized processes, your statistics are just going to tell you it's a mess, right? So you have to have a standardized process. Once I get that, I can launch really into start doing the kinds of things that Six Sigma, Lean, and some of the other techniques are designed to do, which is quantitatively manage the process and start optimizing the way it works, looking for inefficiencies, looking for places where I can tighten it up, where I can sync it better, where I can eliminate sources of waste. Now, having done that, it may not be sufficient for the kind of business we're in. We actually may be in a very competitive business, and our process is not competitive enough. That's fine. That's what level 5 is about. I now need to innovate. I now need to do something, a new process, a new set of tools, better ways to train people, or something that fundamentally changes my results. So this was the maturity model. It's been upgraded into what's called CMMI, which integrates system engineering and software engineering. And I'm going to show you some data in a minute. When it was put in place, it made a tremendous difference in cutting rework and in improving productivity. To give you just a 4-word, simplified way to understand this you can take home: stabilize, standardize, optimize, innovate. Now, I know level 5 is called optimizing because we made a mistake. But that's basically what we're doing: stabilizing the work so that people have a chance to do professional work, then standardizing it to get an economy of scale across the organization, then optimizing it to really drive as much efficiency as we can and eliminate as much waste, and then innovating where we have to get a more dramatic result if we're in an environment where we need it. That's the CMM. How did it work? Medtronic was one of the first companies to adopt this in the medical device world. Unfortunately, don't have their data. But they had a fairly dramatic result, and they've been pretty much committed for a long time to quality practices. And they had a very, very effective CMM program in place in some of their device areas. This is actually from Raytheon, and the reason I'm showing you this, even though it's defense, is that because it's a government contract, they were required to record their hours, and they have to do it accurately by law. If they spend the hour, they have to record it, even if it's overtime. And so they had a system where they recorded what's the cost of doing it the first time, what's the cost of rework if you messed it up and made a mistake the first time, what's the cost of your testing activities the first time you run the test case. If you have to rerun it because of a mistake, then it goes into nonconformance as part of rework. And then the cost of training and other things we're doing to prevent mistakes. And what they found as they went from level 1 up to level 4 is they dramatically slaughtered rework. They eliminated waste. This is a pretty common number I see in low maturity organizations. About 40% of all the work is waste. It's just rework. I made a mistake. I've got to understand it, redesign it, recode it, retest it, and hope I got it right. It runs between 30 and 50%, but 40% seems to be a pretty good average across the companies I've seen rework numbers for low maturity organizations. As they got stabilized, as they got their projects stabilized with good project management, they cut that in half because developers weren't running like crazy trying to build stuff. As they got up to standardized processes, they cut it almost in half again, and most true high maturity organizations are down in single digits for rework, which means they're dramatically, the productivity goes up by a factor typically of 3 to 4 as they get up in this range. So it's fairly dramatic. The quality of what they're delivering is better dramatically, sometimes by, true level 5s deliver 100 times less defect density than guys down here. I mean, that's been shown with things like Space Shuttle and others. And they also end up reducing the percent of effort that has to go into testing and these other improvement activities. So it's been fairly dramatic when it's done right. You can buy a level if you want to. There are assessments where, I call it the Wheel of Fortune version of an assessment. If you know which assessor to go to, the Wheel of Fortune, y'all watch the Wheel of Fortune. I'd like to buy, okay, Pat, I'd like to buy a number. I'd like to buy a 5, right? And there are assessors that you can buy a 5 from. But the guys that do this for real, get real results, have gotten real results. There comes a point where they've pretty much hit the end of the runway and they need to take the next step. Now, how would this apply to healthcare? We went in and I'm going to look at an enterprise value chain in a large organization that delivers systems to hospitals and clinics and other kinds of large healthcare organizations. And they were spending roughly 8 digits every year settling claims against their implementations. It didn't work right, or you didn't deliver what we ordered, or this, that, and the other. And they had a team of about 40 lawyers that spent all their time fighting with their customers over claims against what was delivered. And so what would happen, and we went in and spent a good bit of time modeling this system from beginning to end, from the bill of sale all the way through the end. And we found that in sales, there were items being left off the bill of sales because the salesman didn't know what a system was. They just sort of built it out, and here it is. And they've had some things in, things they forgot because, again, they don't know systems. But they would slam these things into the legal organization where they have to turn this into a contract so they can now book the work against that quarter and recognize the revenue so that the VP doesn't get fired for missing the revenue targets. But all of a sudden there's a lot of rework because people in the legal organization, hey, there's stuff you left out, there's stuff you forgot. I can't build this in the contract. You've got to go back and do more stuff, and the legal people have to do it, and all these other kinds of problems. And then, again, legal people don't know systems, so they do the best job they can, and then this goes into provisioning where they actually have to implement the system from the components they have and other systems they built in the past and reuse what they can reuse. And there's a lot of requirements that never got stated, so they're now going back and doing a lot of rework trying to understand what did these guys really want. And then finding out we implemented something that wasn't exactly what they thought they had ordered, and so now we're going back and doing more. And so the rework grows and grows. And then finally we deliver the system. Oh, and by the way, as we go from here to here, they take the information in the CRM system, which said, build me a system to manage the clinic, and they put it over, hand enter it over into the ERP system, which lists all the components required, and so it suddenly becomes not a system, but a whole bunch of pieces, right? And so the customer never, I thought I bought a system, and you're telling me I bought an interface, and I bought a database, and they have no clue. And so the bottom line, it comes, and there's lots of fights over the invoice, and finance and legal have all these people spending time fighting over this. So the bottom line is the rework builds and builds and builds because a problem started up here and cascade and compound down the system. And when you model this, if you go in and build a model of that workflow, it was just really clear. One of the solutions, a very simple solution as they started seeing the problem, was let's put a technical person up here with the sales folks and have them build a bill of sale. And lo and behold, in the division they did it in, they cut their settlements down to near zero. Right? Because now the invoices were more correct and the rework was slashed dramatically all the way down. Now, the one thing we were shocked at as we continued to interview people and model this thing and talk to people is one name kept coming up over and over and over again. People didn't know who the senior executives were. Everybody in the building knew who, I'm going to talk about that in a second, knew who Cora was. And Cora was right there where this stuff had to get turned from a bill of sale into a contract that legal could deal with. And there were only about 4 people. Cora was the senior one. Cora knew everything about how to translate these technical things into legal things, and nobody else really did. Her cohorts could do the simple stuff. She was the only one that could do the complex, large systems. Therefore, everybody in the building knew who Cora was, because if Cora didn't get her work done at the end of the quarter, they didn't make the quarter. They couldn't book their revenue. And Cora had all this. She was basically a one level above a clerical person, right? But everybody knew who she was, and she had most of the power in the organization, although she never really exercised it. And for the last 3 or 4 days of the quarter, she would basically live in her office day and night. And there were jokes about all the sales guys lining up with bouquets of flowers and chocolates and whatnot to convince her, please do mine first so I can get my commission this quarter, as opposed to have to wait. So, a huge bottleneck in the system that normally you wouldn't catch if you didn't model this in a way that captures some of the human element in addition to all the technical things of the workflow. But this was a massive bottleneck that Cora was and if she ever got sick or quit, they were in real trouble. No one else had the knowledge. So, bottom line, when we're doing lean analysis, we're now looking at this cascading rework, these inefficient practices, overwork and bottlenecks in these kinds of systems. So this was in a system development situation that was causing some real pain and huge, huge settlement losses for this organization. Now, can we do this kind of thing in healthcare? It's being done now. A lot of you are doing this, trying to model what's going on. But it also, can we apply the maturity concepts to healthcare? And absolutely. And I'll give you some examples I've had to live through. Level 1, you go in, there's inconsistent processes, there's inconsistent management. People are in an environment where they're overworked, they don't have adequate staff, they don't have adequate resources, they're making lots of mistakes. And if you went in to see why are mistakes made, you would probably find these classic level 1 problems are behind an awful lot of mistakes. In this eye, I have 1 replacement lens, and in this eye, I have 2 replacement lenses. When I went in for the first one, they had slots for 40 people to get their lens replaced that day, and the surgeon had allowed 54 people into the process. Right? 54 of us were going through this when there's only time for 40. Right? So the nurses were going crazy trying to get us in and out, and stuff stabbed in our arms and through recovery and all this. And so when I got in for my turn, they sent me in the operations room, and the ops nurse threw me out because they forgot to dilate my eyes. Right? So that was cool. Then I go through the procedure, and I'm on the way home. I'm kind of groggy, but I'm on the way home. My wife, who's driving, looks over and says, "Bill, what's that in your arm?" It's just the needle they did the IV with. What? Yeah, they sent me home with the IV needle still in my arm, right? Because nobody had the time to check me out before they released me. So that's the kind of classic problem you get in a low maturity level 1 environment. So stabilize local work, right? And local work doesn't mean the hospital. Local work is the ward or the doctor's office, right? Each work unit has to be stable for the people in that unit to do professional nursing or professional, medical delivery or professional pharmacy or professional whatever they're doing. So it's just simply, and no system is going to solve this problem if you're in this environment, because people are not having time to even use the systems properly. They're running crazy. And then once we get it to where at least it's stabilized, then we can start seeing what processes can be made common, in terms of the way we represent medical records, the way we do various things, the way we deliver medicines and whatnot across the facility, and standardize those processes. This is a place where MBSE really works well, because I've now got reasonably standard processes. What MBSE will tell me down here is the fact that we've got too many different ways of doing the same thing, and the system's going to be chaotic because I've got 18 different ways of filing information, or 18 different ways of delivering things. At least here, now we can model a simple system. Assuming when I'm in this environment that I can do a model and I'll have one model I can apply to the entire hospital, and a lot of people assume that is nuts, because you're going to oversimplify and people are not going to want to use it. In this environment, the model is incredibly complex if you do it well, because I've got 18 different ways to do the same thing. All of a sudden here, when we can get the process more common and more standardized, all of a sudden the models become much, much more effective. The systems become less complex, less prone to defects, and an awful lot easier to change over time, right? And then I can go in and start doing the things we would do in a a Six Sigma lean type environment where I'm really statistically modeling these processes because I have standardized processes, and the statistics make an awful lot more sense. And if I have to innovate, then we can go in and innovate and really radically at new technology, new ways of doing patient records, new whatever, to fundamentally change the overall outcome for the patient. But this is a maturity concept applied to healthcare to improve the entire environment. And as the environment improves, the ability to use techniques like MBSE is going to have much, much more dramatic results. And systems will be much more effective in transforming healthcare as we get hospitals, clinics, doctors' offices to move up this chain. The reason I have two here is this is the first one the guy did when they kind of put the IV in my thing and sent me home. And his office was understaffed, grossly overworked. They just wanted to take a quick measure. They didn't care if it was accurate or not, right? And so they put a measure in, and I came out with, this eye was, this eye later on was 20/25. This eye was 20/60 because of the lousy measurements. So it was, whoa. It was kind of like, oh, this must have been what it would have been like if I'd tried LSD in college. Just whoa. And so I went to another doctor. I finally went back and started researching who really is the top guy and who has the best reputation, and I traveled to another city, and this guy had full staff. He had 2 different people measure it, 3 different people calculate the measures. Then they called the lab to get them to recalculate the measure. That's a minimum level 3 environment, and they now have both of them are about 20/25. So, but it took 2 in this eye to correct it because of the understaffed, overworked, and they didn't give a dang in the initial office. So now I'm going to switch to that. That's the process side, both process in the development organization and process in the environment you're trying to put the system. And so the maturity of both of those is going to tell you something about how easy it will be to get a system modeled and how effective that system will actually be in practice. And let me go back here. In a low maturity environment, down here, what's evidence-based anything going to tell you? Damn near nothing. Because the evidence is so contaminated by the fact that people didn't have time to do it in a professional way, you don't really know whether the method worked. I would say that in this environment, having a lens in your eye doesn't change anything. I'm still half blind with the thing because they did a lousy job. So as we go into the product quality issue, this is the ISO standard defining the different kinds of attributes that you would want to model in a product. And as we look at studies, and this was a major study by the National Council of Engineering saying that the fact is if we want highly dependable software, certainly we want that in the healthcare world, especially in medical devices, the fact is you can't get there through testing. It just costs too much. There's no way to write enough test cases to ensure that under all possible bizarre conditions you're going to get a good result. And the problem is that the correctness of code is really the weakest link, the correctness of the components. It's often the interactions in the components that you didn't anticipate that cause the biggest problems. Diomedes Spinellis is one of the absolute leaders now in software engineering, and he's saying, look, the biggest problems are not the functional issues that you screwed up. The biggest problems are these non-functional issues, reliability, security, performance, all these other issues. These things are the hardest things to test for, because how do you have one test case that tells you about the reliability of a system if it doesn't trigger one of the conditions that crashes the system? So we really need the ability to associate code to these non-functional properties, and we need tools to do that because these systems have gotten more complex than the human being can understand. So one of the powers of model-based software engineering tools is they help us attack that problem. They can't do all the analysis, but they can do some of the analysis and find certain kinds of problems at the architectural level that people are going to have a hard time understanding. So I'm going to have to speed through the last part here. The biggest problem, as I said, are these architecturally complex defects that link across different components and different layers. They typically only account for 8% of the defects in the system, but they account for over half of the effort you spend in trying to maintain and fix the system. Right? So they're uniquely bad. Why are they uniquely horrible? Because it takes 20 times as many fixes to eliminate one of these things, because you're having to go all over the system to fix it. So the more we can have tools up front that help us model the architectural issues in the system and capture those before we commit to code, right, the cheaper it's going to be to build the system and the more accurate it's going to be. And it typically takes us several releases to find all those 20 fixes and get them all in the code before we have a system that's free of defects. So we have these things called architectural hotspots. It ends up there are places in the code that are so bad that a lot of these multi-component defects run through the same set of modules. And if you kill those modules, it's the best roadmap you've got. The really defect-prone, hardly designed components in the system, rewrite those. Don't fix them, rewrite them, because it's probably somebody that didn't understand what they were doing, as in Therac 25, that built those, and that has a huge impact on the overall quality of the system. That's been true at system after system. So this is the question about agile methods. We've got a lot of data in CAS. We have a technology that analyzes these architectural coding flaws and structural flaws in large systems. There's 5 basic things we look at: robustness, which is reliability, performance, security, changeability, and understandability, right? And we've got, this is all in a Java environment. We got people to tell us what kind of method they were using, and consistently across every area of structural engineering, every area of structural quality, the mix of Agile and Waterfall was superior to Agile and superior to Waterfall. Now, these are large business critical systems. This is stuff that banks, insurance companies, transportation systems, energy systems rely on. And what's the notion of the mix of Agile and Waterfall? It means that we spent time up front modeling the system and dealing with architecture and design issues before we started jumping into writing lots of code, right? And so it says modeling the system first has a dramatic impact, a significant impact in large critical systems on the quality, the engineering quality of the system that's produced. And that was consistent across every area of structural quality that we looked at. So there's also, you see there's something called other. The other tends to be methods like IBM's Rational Unified Process, DSDM, and those methods also put a focus up front on modeling. So we have pretty definitive evidence that spending time up front worrying about these architectural design issues has a significant impact ultimately on the quality of the system that's delivered to the users. So I'd end by saying we have this consortium, OMG consortium, called the Consortium for IT Software Quality. We're focused on building measures, standardized measures through OMG that you can use for measuring the quality of code, and these can be used in contracts and a number of other kinds of issues. So we're really very much focused on trying to build measurement from the code for the critical aspects, engineering aspects, structural aspects that any good system ought to achieve. Thank you.